Oh, yeah, I can
Oh,
hear
yeah,
you
I can
now.
hear you now. Okay, thank you. All right, so we use the exponential function to model the middle part. And for the other two segments lower than certain field current or certain flux linkage, and we use linear function. Beyond a certain point, we also use another linear function. So to characterize this curve, and we need 5 independent parameters. So we need the coefficient for the exponential function and another coefficient b in the exponent, and we need the boundary values of the middle segment, and we also need to know the slope of the top segment. At the end of the Tuesday lecture, I used this model from the software TSAT. TSAT is a transient security assessment tool made by Prof Lab. I use this one as an example to show actually we have covered everything of this model. So we have those two equivalent circuits, and each consider 1 stator winding and 3 rotor winding in each axis. So the bottom section is really about the saturation characteristic. So there are 5 parameters which correspond to the 5 ones we talked about. Okay, so if you want to do the transient stability study or do time domain simulation for signal generators, this can be the most accurate model you can utilize. And you are supposed to understand everything in this page. Some notation may be slightly different from my lecture, but you should be able to understand. Okay, so if you are able to estimate the parameter, you can build this model for your study. And this is the most accurate model you can see for stability study. But maybe there's a more accurate model for other areas, but this is the most accurate one we need to know. But if you don't use the Prof Lab TSAT, but you use PSSE from Siemens PTI. For instance, this is their model provided for ceiling pole rotor generator. So JEN stand for generator, IC stand for ceiling pole rotor generator, E stand for something about excitation. So we'll talk about that later. But this is a very fundamental ceiling pole rotor generator. In this model, it utilizes some different parameters from the TSAT model. So in the TSAT model, you just model the inductance and resistance of each branch. But in this model, you see there's many things like T, which stand for time constant. There are some like T single prime, some T double prime. For the inductance or reactance, they use like SD, SQ, or SD prime, or SQ prime, or double prime. So those are different from the TSAT model, but we are going to talk about this model shortly in this lecture. But for this slide, I want to take a look at the saturation. So in the table, the last 2 parameters about saturation. Okay, so instead of using 5 parameters, and this model only needs 2 parameters. So how can that happen? I'm going to let you know how you can generate an equivalent model of the one we talked about using the 5 parameters. So if you go to the manual of this model, which actually came from another textbook, a very classical textbook by Anderson. So Quinter's book is Power System Stability and Control, and this book is Power System Control and Stability, if I remember correctly. But those 2 books are very important books. For instance, like IEEE 3 bar system, IEEE 3 generator, 9 bar system, and there's many other models came from that book. Actually, you know, the PSSE also follow the same model on saturation from that book. So the figure is from the book. A model how the terminal voltage change with the field current. So assume similarly at the beginning when the field current is low, so the voltage will change as a linear function, but beyond a certain point, it will increase slower than the due to the saturation. And this part of function can be modeled by exponential function. So the two parameter IS1.0, IS1.2 are defined as follows. So IF0 is actually nominal field current for normal condition. So you can draw a vertical line intersect with the straight line at the point. So that point corresponds to 1.0, which is nominal voltage. But if you have a saturation, if you increase the current beyond IF0 to IF1, so you see there will be a gap. Okay, that gap is called S1.0, normalized to the nominal current. If you further increase current to IF2 or IF3, so you're going to see a bigger gap. So if you increase the voltage to 1.2, maybe 20% higher than the nominal voltage. Okay, and this curve assume lower than 80% of nominal voltage, we can ignore the saturation. All right, so now the formula to calculate IS1.0, IS1.2 is IS1.0, both actually about the value of a certain function SG. SG just model the deviation of this curve from a linear function. So IS1.0 basically just how the IF1 compared to nominal current. So that gap will be so normalized regarding the IF0. So that will be a ratio. So this one is like percentage or ratio. The IS1.2 is also the same function, but taking the value will increase current to IF2 and IF3. So normalized by the IF2, so you get the second ratio. Okay, that's how the definition about the saturation in this manual. All right, so then if we use exponential function to model the gap, how the voltage deviate from a non-saturated terminal voltage, we can assume exponential function. So this exponential function already defined. There's a two boundary point, one is 0.8, which is similar to psi t1 on the right figure, and 1.2 is similar to the boundary point of psi g2. Okay, so only the part in the middle will be modeled by this exponential function. So which is like we assume just psi t1 is about 80% of the nominal flux linkage, and the psi g1 actually the psi t2 is actually assumed about 20% higher than the nominal flux linkage. So we can solve AG and BG from that equation by plugging the 2 points into that curve. So actually, this will give you the value of the AG and BG. So if you know that the value in the table about S10, 1.0 and S1.2, so you can use those formula to calculate AG and the BG. So you just simply let the A and the B in the Quintersburg model be the same as the AG and BG. Okay, then for the two boundary value, we just simply take 0.8 and 1.2. And this ratio basically just means you need to calculate the difference between the linear and the two linear function. So which will be, you can use a point here to calculate the ratio of change. So that gives you all the values of 5 parameters. Okay, so it's very rare for you to do such calculation because when you do stability study, if you use that model, your model will be from some power company. So already give you the data, so you just go ahead to use data. But just in case, if you have the model from a TSAT, but now you want to utilize, like for example, if you have this model, but you want to use in some other software which is based on the second model, you need to know how to do the conversion of the data. Okay, let's move forward, and we can quickly talk about this example in Kunder's book. To using the formulas we learn about the steady-state analysis. So for it's still same generator we have studied. So it's the power rating is 555 MVA, so which can be the power base. And the 24 kV is actually the line-to-line peak value of the voltage. 0.8 power factor will tell you in the nominal condition how to calculate active and reactive power. So 3600 revolution per minute, which is the speed. So from this high speed, actually you can know this is a round rotor generator. And the following give you some parameters, typical value of parameters. And from, if you compare LAD and LAQ, they're very close. So which confirm it is a round rotor generator. Okay, so in this example, you need to calculate the following things. First, you'll want to calculate the internal angle. The internal angle delta I is not the rotor angle. It's actually the QS is relative to the terminal. So in the phasor diagram, if you draw the terminal voltage at the terminal of the generator connected to the external system, and this the QSs will be leading the terminal voltage by this angle. Definitely, if you know the reference angle in the power system, and so you add the terminal angle by delta I, that will give you the rotor angle, the true rotor angle. So want to calculate the following voltage, current in DOQSs for different windings and also flux linkages, and we want to calculate air gap, torque in per unit. So next, they assume the saturation will reduce the LAD or LAQ to 83.5% of the unsaturated value. So we need to calculate the actual LAD and LAQ. Okay. So next question is, remember in the last lecture we have the most accurate model from the two circuits from for DSs and QSs. Then we merge the two circuits into the same circuit, which is simply just internal voltage, EMF, electromotive force behind the resistance and reactance. If we use that circuit to calculate the angle, compared to the accurate angle, let's see how the difference is. We learned for the round rotor generator, that difference can be very small, because for round rotor generator, the synchronous reactance can be utilized as either the SQ or SD. Remember in this slide. So when we come to the last single circuit equivalent, so this reactance can be either SD or SQ. So if those two are pretty close, we can use either one to do the calculation. For that specific example, we want to use SD to calculate as the synchronous reactance. All right, so before we start calculating anything, I want you to try a quick calculation for those values. The first one is if we compare R1D to the RFD. R1D is the resistance in the first damper winding, right? In DSs. RFD is the resistance of the field winding. So this value must be much larger than that one. If you compare for those typical value, R1D is 0.028, RFD is 0.0006. Okay. So that's true for most of the well-designed generator. Why? Because RFD will create some loss. So it's supposed to be low. You need to minimize the resistance of field winding. But what's the function of R1D? R1D is to damp the oscillation. It's supposed to be high. Because with damper winding is made by either the squirrel cage using some material with like high resistive material, or it should be made by some if it's not squirrel cage circuit, it will be some special material to to convert the oscillatory energy into the heat. So this one's supposed to be very high. So that's very true. And second, I want you to compare two ratios. The first one is the L to R in the field winding circuit, and second is L to R for the first damper winding circuit. So both value actually came from the DSs, right? So LFD divided by RFD, what was the value? So it will be this one divided by that one. So we have a 0.165 divided by a very small number. But L1D divided by R1D, you have this L1D for this generator is close to the LFD, but R1D is much smaller, much bigger. So that will make the first ratio be much bigger than the second ratio. So keep this in mind. Okay. Similarly, you can, okay, for this one, you consider second damper winding. So when you consider separate damper winding, if you calculate the ratio for the first one, the second one, first one is much bigger than the second one. So if you ask me why this is true, because that's how we number them. We just make the which one which ratio had a bigger value as number one, which one has a smaller value as number two. Okay, because when you add a second damper winding, it's supposed to model a different dynamics. So if the second damper winding has similar L and R value, you don't need to add second one. You want to add a very different one. So that give you, that make a R2Q to be much bigger than R1Q. So this one's supposed to be bigger than that one. So they will create a very different dynamic. For instance, R1Q will help the damp oscillation at a certain frequency, okay? And the second damper winding will help the damp the frequency in a different range. So those assumptions we can keep in mind. So it will be useful for this lecture. Okay, so we can go ahead to do the calculation. So from a power factor, we can get P value, Q value. If we assume terminal voltage to be 1 and terminal current also to be 1. So both are operating at nominal condition. Power factor angle is 25.84 degree. To calculate the internal angle, we can use this formula. We already proved it using the phasor diagram. Okay, so we can just go ahead to do the calculation. First, we use the original LED, LEQ, and multiply by those ratio, which due to the saturation. So it will be reduced to lower value. Okay, so those values need to be utilized to calculate LED, LEQ. LED, LEQ basically just LED, LEQ plus LL. So this will be the result from that equation. So it tells you the angle is 39.1 degree. So then you just utilize the angle. This angle just indicates the direction of the Q axis. So you can calculate for the terminal voltage as a phasor. So ED will be a component in the D axis, and this will be Q axis. So D axis correspond to real value, and Q axis correspond to imaginary value. Okay. Oh, so here sine, cosine, because the delta is defined to be the angle in the Q axis. So ET will be leading the EQ. If we go back to that phasor diagram. Okay, so this is ET, right? So its projection to Q axis will be EQ, and projection to the D axis will be ED. So EQ will be ET multiplied by the cosine delta I, and the other one will be a sine delta I. Okay, what else? To calculate ID and IQ, you can utilize the delta I, but also consider the power factor. Power factor angle. Yeah. All right. So the last one is just IFD. It's a field current. To continue the calculation, so those are basically just from that slide with all the equations for static condition. And under static condition, all the damper winding currents are 0. To calculate R gap torque, and also base, you can calculate the electric torque, mechanical torque, electric torque, and also using the saturated value of LAD. LAD multiplied by omega will be SAD. So in per unit, that will be same. So you're going to calculate the EQ. So the last equation is from that slide. It's about, let me go back. The definition of that, the EQ. That is from this one. But for this case, it's round rotor diameter. We ignore this part. So the EQ, the magnitude EQ will basically just proportional to the field current, IFD. So the ratio will be SAD. SAD is LAD multiplied by omega R. All right, so next we want to utilize this circuit to redo the calculation for the angle and also for a number of other quantity on the circuit. First of all, if we use this circuit, so we just treat SD to be same as SQ. And let's just assume we directly let the signal's residence XS be SD. So we'll take SD value. So this value is actually SD, not SQ. But because it's very close to SQ, we just utilize this one. We only just use this circuit. We only have one equation. The EQ will be equal to the terminal voltage plus voltage drop. And for this case, we ignore resistance. So it will get a phasor for this EQ. And the number will be the length of the phasor, and the angle will be basically just delta I. Because delta I is actually the angle of the EQ relative to terminal voltage. For terminal voltage, we assume that one to be the reference with 0 angle. So the delta I from here will be 39.6. So if you compare to the accurate angle we calculated from previous slides, that's very close. Okay, for round rotor diameter, it's safe to use this circuit, just single circuit, to do all the calculation. So field current, if you use this voltage divided by the SD, will get this value. So this is the field current we calculated from this circuit. So that is also very close to the value, accurate value. So the difference is only 0.001. All right. So this is everything about steady state. Any question? Yes.
Delta I has XQ and plug in LQ.
You mean the accurate formula?
Yes, first part.
Okay, let's see. No, this is SQ. Yeah, that's no. This is accurate formula. We just use the accurate value. So if it says SQ, we'll use SQ. It says, oh yeah, this one only need SQ. Yeah, so we use SQ. So LQ is actually XQ in per unit. Same, yeah. Frequency assumed to be 1 because that's steady state condition. We assume frequency to be 1. For steady state and 60 Hertz. So this guy is also same as EQ, SQ in per unit. So in the formula, we use SQ. So here we also use SQ. We didn't use SD. So the first one will be SD in per unit. Okay, any other question? Yeah, let's move to the dynamic. Okay, so when we talk about dynamic, we focus on something different from the steady state behaviors of the power system. So if we assume any disturbance on the system following the disturbance, and if you measure, for instance, the instantaneous current in phase A, you will see an oscillation. If now we assume the current change at the frequency of 60 Hertz, but you see the first number of swing will be much higher because that's represents some transient dynamic after the contingency. But after a while, the waveform will go back to the steady state value. So when we talk about the steady state quantity, remember in the quiz question we mentioned steady state condition doesn't mean every variable is constant. It just means we can ignore the difference. So we basically, because those steady state waveform, they have very close the magnitude, and such as we can ignore the difference. So that's steady state period. But if you look into the waveform of current is still dynamic, but it's not very interesting dynamic. But if you take a look at the period, a short period right after contingency, you will see the waveform decline. And you can further partition that period right after disturbance into two periods. First one is called sub-transient period, which is much shorter. And the second one is a longer, which is transient period. Okay, so how do we differentiate those periods? For the sub-transient period, and we can start from the initial value, and we draw an envelope that actually tell you the fuzzy dynamic from beginning, how it can decline until the steady state condition. Transient, so that usually just take a few cycles to decay. So if you want to capture sub-transient dynamic, you need to look into the first several cycles. So how long is one cycle? How many seconds?
1/60.
1/60, which is 0.017 second. That's one cycle. So if we talk about several cycles, let's say 6 cycles or 7 cycles, that's about 0.1 second. Okay, so which means sub-transient dynamic usually will be finished within 0.1 second. Beyond 0.1 second, that becomes transient dynamic. So after the sub-transient dynamic decays, after 0.1 second, we notice the waveform still not reached the equilibrium or the steady state yet. So it still takes a longer time to really become equal magnitude waveform. So that time usually take several seconds, okay, to tens of seconds. So that's called the transient period. So you will see slowly decaying waveforms until the steady state waveform. So sub-transient dynamics usually is finished within 0.1 second, and transient dynamics are finished within maybe, let's say, 10 seconds. Okay, depend on the system. And finally, when the waveform become equal magnitude, that value, if you take that value, that will be the you can calculate the current and voltage phasor values. So that will be the steady state value. Okay, so for those three types of dynamics, we need to define the names of parameter related to those dynamics or categorizing those dynamics. So for any parameter which can help categorize the sub-transient dynamic, we just call those parameters as sub-transient parameter. So usually we use double prime. So when you see any notation with double prime, which means it's attached with a sub-transient dynamic. If you see some indulgence with double prime, this is sub-transient dynamic. Or there could be a reactance, or could be a time constant with double prime. for transient parameter, which means there's some transient dynamics. So they can be categorized by L prime, S prime, or T prime. So which means transient dynamic parameter. Okay. How about for steady state behavior of the system? They will be categorized by another set of variable L, S, T, and we don't add anything. We already utilize those values, right? Remembering how we already defined LD, LQ. Those are basically just the parameter we utilize to model the steady state behavior. So we're going to introduce the single prime or double prime parameters to categorize transient and subtransient dynamics. Okay, before we introduce those parameters, let's just assume what if we don't categorize those dynamics? We just go ahead to use the most accurate model to do some calculation. Because we already have that model. We have the very our first good model with all the we have the voltage equation, the flux linkage equation, and which involves some matrix, and every element in such matrix is constant, right? So that is our good model. We can utilize that model to do some simulation. For instance, we can add a three-phase fault to a generator. So let's assume the generator we have short circuit connecting all the three phases of the terminal, and assume we have all the parameters, and such parameters are all constant. So which this is good model. We definitely can do such calculation. Okay, we just utilize the voltage equation. If we spell out everything in the voltage equation, so it will be voltage vector with the stator winding, rotor winding, and we have resistance matrix and the inductance matrix. So this is a differential equation. If we know the initial condition, we can integrate the equation to calculate the waveform of voltage or current. But definitely for this case, since we have short circuit, the voltage, terminal voltage will be always zero, but current may not be zero. For this case, we consider starting from no load condition. For no load condition, the initial value for all the three currents will be zero. After power transformation, if we change to the frame of zero DQ, all value also are zero. Okay, for balance condition, the three voltage will be always zero. After transmission, still zero. And we can we know some initial value. For example, for the field winding current, we know this is we can do the calculation because the table gave you the field winding resistance, this 0.4 ohm. Also, it gave you the field voltage, which is 400 volt. So you use this voltage and that resistance, you can calculate the field current, initial field current. And for this case, the initial damper winding current have to be zero because it has no disturbance before time zero. So we need to solve this equation for current. So we move the derivative of current to the left and everything to the right. So this will be first order differential equation to solve. We have all initial value. Okay, you just need to do the integration. If you know how to use MATLAB to integrate this equation, or you can do it manually, you are going to get those waveforms. The field current, the first one is about the field current. So we start from 1000 initial value. Right after the fault, it will suddenly increase to very high value because the terminal has short circuit. Okay, so the voltage due to the short circuit, the field current will try to recover the current of the terminal, so it will suddenly increase the field current. But because the fault is still there forever, so eventually the current will still go back to the original value. The second figure is about the terminal currents IA, IB, and IC. So because for this case, we assume the fault happened when the theta is exactly 0. So that will make some of the instantaneous current be more symmetric depending on their initial value. So you will see you will have suddenly increased instantaneous current, but after some time it will gradually go back, okay, to the steady state value. The second one is actually the current in the 0 DQ frame. Okay, for this case, the fault is balanced, so we don't draw I0, only draw ID and IQ. So you can tell the ID will finally stabilize some value higher than 0, but IQ will go back to 0. So this is because we start at theta equals 0. If you start at different value, you will see the value of the ID and IQ be slightly different. Okay, because ID IQ really tell you the initial location of the phasor, the terminal current. And this is the damper winding currents. The damper winding currents will increase right after fault. Okay, this one is a Fourier transform of the current. So you can tell the fundamental harmonic is still 60 Hertz, but because there's some fast dynamic, you also have some higher harmonic. Okay, I'm not going to detail to analyze why the waveform looks like such a plot. The purpose of using this example to show we don't really have to categorize dynamic into a steady state, transient, or subtransient, because we already have a good model. You can integrate the model, right? You can get any waveform you like. So that's exactly what we call the electromagnetic transient simulation does. So for someone who really want to study the protection design of fast dynamic, they can really just utilize such equation. They don't have to define, categorize the dynamic into a different category, because any categorization will introduce some error. You have to, for some dynamic, you have to tell whether you categorize this one as slower or as one as faster. But if you don't want to introduce any subcategory, you just want to calculate the waveform, those equations are good enough to you. Okay, so for protection people, for anyone need to do electromagnetic transient dynamic study, they can utilize such equation to do the simulation. But for stability study, this is too complex. We don't really want to integrate all the 6 equations, right, for the current. We want to have simpler model. What if I'm only interested in the dynamic, in transient dynamic? Any dynamic in the first 0.1 per 0.2 second not important to me. Why do I have to calculate that one? Can I directly jump over to here to get how the dynamic can impact my system? So that's what we're working on right now in the following slides. Okay. So the next example from Sadet's book, this talk about another unbalanced fault. It's line to ground fault. For line to ground fault, we assume only phase A has short circuit to the ground. Also, we consider no load condition, so the other phases will have still 0 current. For the phase A, the voltage will drop to 0. Okay, so for this case, because it's unbalanced, it may not be very beneficial to utilize power transformation. Because power transformation is useful, especially for balanced condition which close to steady state, right? You can simplify. If the system is unbalanced and also it's not far from steady state, there's not many differences between the equation in the frame of ABC or the frame of 0 DQ. Okay, for this case, we know the phase A voltage will drop to 0, so we pick the first equation. So this is from very beginning equation, voltage equation, right? You see all the L will be theta dependent value. Okay, we use this one to do the integration. I just do some So this step, it just introduced the formula for each L. We already derived each L as function of theta. So we just plug in the formula, will have this line. Okay, so each one, you see there are many theta dependent functions. We need to solve the following voltage equation. For this case, because phase B and phase C are actually open the terminal. So there are not many interesting things to be analyzed because the current will be 0. So we only include this voltage equation together with 3 voltage equation on the rotor. We only solve those 4 equations, which are enough to tell us some interesting dynamics. Okay, so the parameter is same as the previous slide, but in the previous slide, may I bring back? It gave you all the value, okay, after path transformation. But right now, we'll do the calculation not in 0 DQ for that unbalanced fault. We only, for the first 3 voltage equation, only just pick phase A. So we may need to utilize those values to calculate those theta functions. Which is basically about how to calculate LM and LX, which are not given by the table. But if you go back to my earlier slides, so when we introduce L0, LD, and LQ, so there are 3 equations to calculate those 3 L's from LS and MS. Okay, and LM. So which means we can utilize those 3 equations to solve LS and LM, which would be this one. So if we know L0, LD, LQ, we can solve LS and LM. What is LS and LM? LS is actually the constant part of LAA, the mutual indulgence between a self-indulgence of the winding A. And LM is the varying part. It's actually the multiplying this cosine 2 theta. So by using the L0, LD, LQ, we can solve those 2 L values. And then we can start integration of the equation. So we can calculate the instantaneous current and instantaneous field current and also the damper current. Okay, so which means using the our first model, we can definitely study any dynamic, accurately study any dynamics of the system, no matter it's a balanced fault or unbalanced fault. But the problem is not very convenient. We don't want to integrate so many equations every time, no matter what dynamic we want to study. Okay, then we need to think about how we can simplify the model. So it will be very beneficial to categorize 3 types of dynamics, and we can come up with the parameter categorizing each type of dynamic. And so, for instance, if you want to study subtransient dynamic, which happened within the first 0.1 second, we can utilize L prime, double prime, S double prime, or T double prime to do the calculation. But if you want to jump over the subtransient period and to study transient dynamic, we can select the parameter with single prime. Okay, so that can make our calculation be much simpler. All right, so now let's talk about how can we categorize the transient dynamic using some parameter. Okay, so definitely to categorize any dynamic, you need to introduce some constant of time or time constant. Time constant means how quickly this dynamic will decay from beginning. We know for subtransient dynamic that decaying time will be several cycles. For transient dynamic, that can take longer than as long as 10 seconds. So there should be something, some parameter telling you, okay, this is 0.1 second, that is 10 seconds. So what is that parameter? Okay, let's start from this very simple circuit with single resistance and single indulgence and powered by a source. a voltage source. It can be just sinusoidal wave voltage source like AC source. And we introduce some disturbance. So we can turn on the switch or turn off the switch. But for this case, let's assume at time 0, we just close the switch. Okay, so you can imagine at the beginning, the current going to the R and L will be 0. But once you turn on and close the switch, the current will gradually go up. And voltage will also change. So there will be some dynamic which only happen for limited time. But after you simulate long enough, that dynamic will be gone. Okay. For this circuit, we only have 2 parameters, one R and one L. We assume the voltage source will be will be this sine function. So we introduce the unit step function. Unit step function means we just start at time 0. Okay, the purpose is just to make this VT apply to R and L starting at time 0. So based on the circuit, we can write down this equation based on the Kirchhoff voltage law, because the voltage drop on the resistance plus the voltage induced on the inductance will be equal to the voltage of the source. So this is first order differential equation. The next step, we want to solve this equation. To do that, we first apply Laplace transform. To apply Laplace transform, R is a constant, so it doesn't change. Lowercase I will become capital I, which is Laplace transform of the current. And L is constant, it doesn't change. For derivative of I, so Laplace transform of any derivative will be equal to S multiplied by the Laplace transform of the current, but you also need to add a negative initial value. Okay, that's by definition of Laplace transform. And voltage, it just become the Laplace transform of voltage. And we move the I to the left-hand side, because for this case, the current can increase from 0. So which like output due to the disturbance of the circuit. So we'll have IS be equal to, we will divide both sides by R. And also we do some simplification and we'll have this one. So will become V divided by R multiplied by this expression. And to simplify this one, we can introduce time constant tau. We define the L divided by R. So, and current will change as a function. So in the frequency domain, it will be voltage divided by resistance, then multiplied by, this is usually called the first order component. Okay. So the first function of this one is just delay the dynamic by this time constant. If you have more L or more R, so you will multiply by more component, higher order component, there will be more delay. So basically what this formula tells is something happened on the voltage will have delayed effect on the current by this time constant tau. We haven't assumed the value of L and R. We can make LR be whatever value we like. We can create a time constant at similar to the sub-transient dynamic or similar to transient dynamic or even to very slow dynamic. By selecting different L and R, we can make a different time constant. So we can utilize this circuit to understand how the transient dynamic or sub-transient dynamic decay is decaying until the steady state condition. So the next step is to use the inverse Laplace transform. Okay. So I don't prove this one. I assume everybody know how to do the inverse Laplace transform. So we'll become this expression. So this one tells exactly how the instantaneous current will change. There are 2 items. I color the first one in green. So this one basically just sinusoidal waveform, the steady state sinusoidal waveform. And the second one is also, it's actually a function of time, but it's an exponential function. This negative sign indicates this decaying exponential function. All right, so you know the first one will be steady state waveform. The second one will be transient dynamic. So the first one will be the steady state component. Second will be a transient component, which is actually DC component. So the IM, which is the peak value of the current, will be equal to, you can actually calculate the IM from the peak value of V, and also this one is the impedance, the magnitude of the impedance. And the gamma here is actually angle, the impedance angle. Okay. Because you already defined tau, tau will be L divided by R. So this one can simply calculate it by arctangent of omega tau. All right, so let's explain a little bit more about what this exponential function means. So E with exponent of negative t divided by tau, what does this one mean? This one means if t is equal to tau, okay, so which means after some disturbance and you have timer, you click until t reaches tau, and this value will become E with exponent of -1. So the value is 0.37. So which means this one decrease to 37% after time tau. That's what they mean. So if a tau is 1 second, this one will decay to 37% after 1 second. Okay, if tau is 1 cycle, it will take 1 cycle to decay to that value. So tau is a time to decay by 63%. 60% is more than 60%, right? It's a majority part. So roughly speaking, tau is the time take to decay majority of the dynamic. Okay. So that's why we can use tau to measure the time duration for the transient dynamic to decay or disappear. Maybe after a couple of tau, the dynamic will disappear. Okay, so using the value from one example on the SADS book, I gave you R, L, and peak value. So you can calculate the waveform. The waveform will look like this one. So this part will represent the steady state component, which is perfect sinusoid. And the first part, the envelope of the first part will be this DC offset will be transient dynamic. So if we color them, this envelope will be the transient dynamic. So will be disappear maybe after 0.1 or 0.15 second. And this magnitude will indicate the steady state value. Okay, so what we learn from this slide. So in order to obtain the waveform of the detailed dynamic, you can definitely use the very accurate model, right, to integrate current, voltage, starting from the beginning of the disturbance. You're going to integrate many equations. For each generator, you have cylindrical rotor generator, you have 6 equations, 6 first order differential equation to integrate. Okay, and if you have many generators, you need to integrate many equations. Another way to simplify the analysis is we can categorize dynamics into steady state behavior, transient dynamic, or even faster subtransient dynamic. In order to do that, we need to define some parameter, such as like time constant, which tell us which dynamic we're really interested in. Okay, and that the next one will be we have so many parameters from generator. We just need to select which parameter fall into which dynamic. So if you have very fast dynamic and which means the time constant is very small. Okay, then we need to know which L and which R will cause this tau. Like for subtransient dynamic, let's say the tau is 0.01 or less than 0.1. we need to figure out which L and which R will create this tau. And those L's or R's correspond to the branches or the circuit, part of circuit, which really characterizing the dynamic of that time frame. Then you can ignore anything else. That largely simplify the circuit only to this one. There may be many other L or R, remembering how many branches we have in the equivalent circuit. But maybe there's only just one L and one R are really important to tell you related to that tau. And eventually we can utilize just a simple circuit to study each type of dynamic. That's what we're doing right now, okay? Any question? Everybody follows? Okay, now let's go back to our equivalent circuits of the generator. We already have the two equivalent circuits in DSs and QSs. I didn't draw the details of circuit, but you can just think about those circuits in your brain, in your mind. In the DSc circuit, we have input, which is the field voltage, right? Output will be the power going to the load or the rest of system. You have terminal voltage or terminal flux linkage. You can use either terminal flux linkage or terminal voltage, because terminal voltage just terminal flux linkage multiplied by P, multiplied by the differential operator. It doesn't matter, okay? But we're really interested in dynamic captured by this network in DSs. So in QSs, there's no input, okay? But there's only just output going to the system with the flux linkage and current. Then next, how many type of disturbances do we need to consider? We need to consider open circuit disturbance and short circuit disturbance. Okay, we need to study at least two type of disturbances. So why do we need to study those two types differently? Because they happen at different locations and make the input or output of the dynamic function be different. Or let me give you one example. So if you add open circuit here, so when you open the circuit, which one will change instantaneously? So you have current and flux linkage. Which one will change instantaneously? When you open this circuit, the current will become zero suddenly, right? But this flux or the voltage will take some time to change. So which means you can define transfer function, which is like the one from previous slide. Okay, from that simple circuit, we want to create. So for this case, the voltage will have instantaneous change, and then we'll call delay change on the current. Then that delay can be modeled by this first order system with some time constant. So then we move to the equivalent circuit of generator. When we open the circuit, the current has instantaneous change and flux has delay change. And we just figure out what that delay is. That will give us some time constant. So if that time constant fall into the sub-transient dynamic, so it will be called sub-transient parameter. If it fall into the transient dynamic, it will be called transient parameter. And for the short circuit contingency, if you add short circuit contingency to those two terminals, the voltage will become instantaneously zero, but current will take some time to change. Okay. So that's why we have to separate the short circuit and open circuit faults differently to study those time constants. We just use DS's network as one example. So when we have short circuit contingency, we have instantaneous change on the flux linkage of voltage, but the current will have delay change through some time constant tau. If we have open circuit contingency, you have instantaneous change on the current, but you have delayed change on flux linkage of voltage through some delayed first order component. But here we use tau zero. Zero just means open circuit to be differentiated from short circuit. We haven't figured out what that tau 0 are, but yeah, we just utilize this idea. Okay. Then we can reasonably guess. So LD, earlier we have LD, which is just a constant value. Okay, if we that only change when you have saturation. But here, if we ignore saturation, or we assume only at a specific operating condition, we already know the steady state value of LD. But here we want to change LD to some function of time. Or in frequency domain, will be function of a frequency. So the LD will change with the frequency. The frequency is to utilize to categorize what type of dynamics. So depending on if S is high, which means it's faster dynamic. If S is low, which means slower dynamic. So LD will be function, okay? And we can reasonably guess LD has to satisfy this expression. Is this clear? Because when you have instantaneous voltage, that will cause delayed change on current. So that time constant is tau. When you have instantaneous change on current, you have delayed change on the voltage. So that time constant is T0, which means voltage divided by current. Let me see. Voltage divided by current, that will be this first order system. And the current divided by voltage will be this first order system. So when you combine both, you have this one. If you have voltage flood divided by current, you have tau 0 on the other side, hand side in the denominator. But if you flip this one, you have current divided by voltage. So tau will be on the bottom, will become time constant. So to model how the LD change with dynamic, it has to satisfy this form. But so far, we don't know what that tau is, but it has to meet this condition. Next, okay. So this sentence is very important. The time constant tau or tau 0 is equal to the equivalent L divided by R of the effective circuit. Effective circuit means you only just pick a single circuit. You don't have to, you can reasonably ignore anything else which are not related to this dynamic. You can make some approximation here. So finally, you only have one L and one R. That one define your tau, and then you in this equation. But definitely, you need to study open circuit and short circuit scenario separately to determine both time constant. Further, if we want to separate the transient dynamic from subtransient dynamic, you have to add another order. Okay, definitely, if you want to introduce even faster dynamic, then subtransient dynamic, you put like a triple prime. You can, if you like, you want to do that, you can. If your generator really present that complex dynamic, you can keep adding the order forever. But typically, we only consider transient and subtransient dynamic. Just two types of dynamics. Any question? All right, so this is very important slide, right? Don't be lost. When we finish this slide, we're done for today. Okay. So those are the two equivalent circuits. So here, just to make the analysis be general enough, the DSC circuit is the same as what we use, but the Q, I add a second branch, second number one. It just make the two circuits somehow symmetric between the D and Q. And that as a side. So I call this branch to be number one, this branch to be number two, but you can definitely just draw this branch, the second branch on the left-hand side. But here, the number one, number two really depend on those two resistances. So why I call the second one to be number two, which means R2Q is much bigger than R1Q. I make that assumption. If both are same, there's no reason to create two separate circuits, okay? Because we're using those two to somehow differentiate different type of dynamic. So those assumptions still there. So we keep those assumptions there. So much bigger, which means if we have any expression, we have number one plus number two, but because the first one is bigger than second one, you're safe to ignore the second one. Okay. So that's what I assume, just to make your equation be simpler. So we create this table. We separate in DSA circuit and QSA circuit. And we consider first, even we have two windings in each circuit, we don't have to consider both. So we understand for some calculation, you don't need to consider both, you only need to consider one. So in each circuit, I create two subcategories, and we can either, like for this case in DSA circuit, we can only consider the field winding, but we ignore that one. So when we consider this one, we just open the circuit of the second one. Okay. Similarly, for the DSA circuit, we have a two damper winding. You can only consider number one, but number two will be open, or you consider both. Next one is we want to identify the time constant for open circuit continuances, time constant for short circuits, and also we want to figure out the inductance in D and Q seen from the terminal. Seen from terminal, which means if this is black box, I just inject some dynamic. Depending on the frequency of dynamic, I measure the inductance at terminal, so that value can change. That will be a function of frequency, right, or function of time. So I want to figure out the value for different scenario, what value the LD or LQ can present. So let's study each of them. Let's consider for this scenario. Okay, we open the circuit and only have field winding for DSs. What that means, this one will be open. If this one is open, what is R? And you open the circuit. Okay, this one has nothing. So this one is not functioning. The LL is not functioning. Okay, let me use my. Okay, for this case, this one is not useful, and this one is not useful. So what is R and what is L? The only R we have will be RFD. Okay, we have two L's. We have LFD and LAD. So they're both useful because they're connected in series. We have this LR circuit, right, with a source which R and LAD plus LFD. So the total L will be LAD plus LFD. The total R will be RFD. If we see the circuit finish this loop, that will be exactly the same as the RL circuit in the previous slide. Okay, let me clean this. Okay, second one. So if we have short circuit, if we add a short circuit, so for this case, we have a line connecting this terminal, but this one is still open. So what will be the what is the total R? Still RFD, right? What is the total L? The total L become first this is L connected directly with R, but it will go through two branches. First is LL, the other is LAD. So total L will be LFD plus LL in parallel with LAD. So which will be this one. Okay, so what is LD seen from the terminal? The LD is seen from terminal if we see from this side. So we first go through this LL. Then we have this LAD and LFD connected in parallel. So that will be this one. All right, so yeah, we finished the first column. Second column. Second column, we add that damper winding. When we add that damper winding and we open the circuit, and we have everything here. And because we know the R1D is much bigger than RFD, which means we can ignore the RFD. So the R will be R1D only. Only this one become R1D. And total L seen from this R1D will be first L1D, then have another two parallel branches. Okay, so now the L will be L1D plus LAD and LFD in parallel. So if we have short circuit, similarly we see from this side we have short circuit connection here. So R1D is still the only R, but L become R1D, first R1D, then go through three branches, right? One is RFD, then LAD, and also LL, okay? So we have three in parallel. And inductance seen from the terminal will be first go through LL, then we'll have three L's in parallel. Okay, that's done. So I don't have to go through the second column is same. It's basically same. Okay. All right, so we have the ratio of L to R for each scenario. Definitely there are some approximation because we reasonably ignore some smaller number when it stay together with some larger number. So we utilize those three assumptions here to reasonably simplify those expressions. Okay, so now we are ready to define their names. So if we use the value from example 3.2, we calculate those values. So we know anything like L by R will mean some time constant, but we don't know what that time constant is. If you calculate the value, the first one is about 8 seconds. So we just call it T single prime. This is transient time constant in DSs for open circuit condition. So that's why we call it TD0 prime, single prime. And we calculate the second one. Second one, the value is 1.3 seconds, and it's in about the same range, right? It's longer than 0.1 second. So we call it TD single prime, which means it's transient time constant in DSs for short circuit condition. And this one we call it LD single prime because it's a transient inductance in DSs. So this is the value. If you remember the steady state value, you remember, I think we discussed at the beginning, right? When we draw we calculate the delta I. Do you remember what that XD is? At 1 point something, right? Much bigger than this value. So you can tell. So when you add some contingency, and the inductance from the terminal suddenly decreases to this lower value, very different from the steady state value. That LD is about 1.5, but now it's become 0.3. And this second column, you do the calculation, the first one is only 0.03 second, right? 0.02. So both are less than 0.1 second. So those two are considered sub-transient time constant. So it's called sub-transient time constant for open circuit condition in DSs. Okay, so this is for short circuit condition. So this is LD double prime. So this value further decreased, is further decreased from LD prime. And if you do such calculation, you see this one, that one also close to that time frame. So you put those both in the transient dynamic time frame, and those two will be in the sub-transient time frame, less than 0.1 second. Any question? Sorry, it will be slightly longer. Let me finish this slide. Okay. So those formula will be good formula for you to calculate those time constant or inductance. So if you read the Quinter's book and they give you the table, they call the classical expression. So it give you those formula. If you plug in each element into the formula, you will get exactly the same formula as the table. Okay, but actually the Quinter's book mentioned those approximate formula, but although they are accurate enough, they're pretty accurate. But if you really want to find even more accurate formula, they give you another alternative. But usually, we just utilize those classical formula in the table. Another thing I have to mention, if you utilize the value from example 3.2 to plug in those formula, when you calculate L, that's same. You will get exactly same value because the parameter from 3.2, if you use per unit value, you will get those exactly same numbers. But when you calculate time constant, you don't get those numbers. The reason because if you use per unit, you are going to calculate per unit time constant. So per unit time constant does not have unit of second. Okay. What is the per unit time constant? The unit will be 1/377 seconds. So for instance, if you calculate any time constant, you get maybe 1 per unit. 1 per unit time means 1/377. Okay. In order to translate the per unit value to those values in second, you need to multiply the calculation by 1/377. So that will give you the value in second. Okay, that's the only thing I need to remind you. Okay, all right. So sorry for a little bit longer lecture.